Difficulty to connect. So I see one of the students cannot connect at the moment. Okay, maybe she will come. Okay, let us start the meeting. Good afternoon, everybody. Welcome to our webinar. I'm Neda Sadouri. I'm speaking from Tehran, Iran. It's an honor for us to have today Professor Veronica Dexheimer as our guest speaker in our first webinar in the new year 2021. Professor Dexheimer is currently an associate professor at the Kent State University in the USA. She receives her PhD in 2009 at the Frankfurt Institute for Advanced Studies of the University of Frankfurt in Germany. From 2010 to 2012, she was a visiting assistant professor at the Gettysburg College in the USA, and since 2013, she's a professor at the Kent State University. She's a theoretical astrophysicist and is mainly interested in dense and hot quark matter. Today, she will speak about exotic matter produced in neutron star mergers. Before starting, let me also add some words to the organization of this webinar. The length of the webinar is maximum 19 minutes plus 30 minutes of discussion. It is okay to ask short questions during the talk, but let us postpone long discussion to the end of the talk. And to keep the internet connection stable, please turn off your video cameras on your computer. So Veronica, you can start.
Thank you. Thank you for the invitation. And I'll start sharing my screen now, but please feel free to interrupt me at any time and ask questions.
Okay.
So I'm going to talk about neutron stars today, and specifically about exotic matter, about the possibility of having hyperons and especially quarks in the interior of neutron stars, and how can we probe if these particles are indeed formed. I thought it'd be nice to begin with a very quick historical overview of the modeling of the core of neutron stars. So the first time that someone thought about a giant nucleus was Landau. And this is a very interesting story because he predicted neutron stars before the discovery of the neutron, about 1 year before. So what he thought was that maybe there could be a giant nucleus, but at that point, people thought that nucleus was just a giant blob of positive particles. So the problem is, if you have a very large amount of positive particles, there's a lot of Coulomb repulsion, and you cannot stabilize this, not even with gravity, because gravity is much weaker than electromagnetism. So he said a very funny thing to say in the previous century, that in the beginning of the previous century, when quantum mechanics was a very important topic of discussion in physics, he said that the laws of ordinary quantum mechanics would have to break down to have a giant nucleus. And people thought this was very weird. And although his paper became famous as the first prediction of a neutron star, someone actually scratched the date. And nobody knew this paper came before the discovery of the neutron. This was just found out by Professor Yakovlev about 10 years ago. So has a very interesting paper on the topic. But after the neutron was discovered, of course, this made sense, because if you can have many more neutrons than protons, you can have a giant nucleus of the size of a city, which is a neutron star. But the neutron stars were all, this idea of neutron stars were only related with the supernova explosions that people had already been documented for about 1,000 years in 1939. And right after that, people already start modeling neutron stars, because since they are, after a supernova explosion, there's no more fuel to do simple fusion like what's happening in the sun right now. So there has to be another mechanism for the stars to fight gravity, because you need some sort of internal pressure to fight gravity. Otherwise, the star immediately collapses to a black hole. So if you don't have fuel for fusion, which is what triggered the supernova explosion in the first place, you need another mechanism. And this mechanism is just simple Fermi pressure, because the star is filled with neutrons and also a little bit of protons and electrons. What happens is that these fermions cannot all occupy the same energy level. You can only stack one fermion spin up and one spin down in each energy level. And if you have a lot of these particles, and we're talking about 10 to the power 53 of these particles in a normal neutron stars, what will happen is that you have a lot of energy that you get from this mechanism. And this is what fights gravity and keeps a neutron star stable for billions of years. But this is a very simplistic model that cannot really describe a neutron star quantitatively. For that, we need not to have just a simple gas, non-interactive gas of fermions. We need strong force interactions. The strong force is much more complicated than the other forces. You have an attractive and a repulsive component in the force. This was first modeled in a relativistic form by Valechka in '74, and this became very widely known as the Valechka model, which is until today is used to model neutron stars. And why relativistic? Because neutron stars, you reach very large densities. And if you don't use relativistic models for the core, what happens that you might end up with a description that describes the speed of sound as larger than the speed of light. And if you try to use non-relativistic models at finite temperature, then it's much worse because you very easily reach an acceptable behavior having the speed of sound much larger than the speed of light. But the way the Valechka model is used until nowadays is with corrections, because a simple Valechka model cannot describe nuclear properties, because at neutron stars, at low densities for neutron star densities, but when you reach densities approximately densities of a nucleus, we have information from the lab. We can measure things like compressibility, symmetry energy, binding energy. So we have a good guidance for that regime. So in order to fulfill these nuclear properties correctly, you have to add at least a few corrections to the Valechka model. But at this point, we're only talking about protons, neutrons, and electrons. The hyperons were introduced in modeling in the same decade by Glendening. And what happens is, if you have enough energy in your star, you have more energy than the mass of these hyperons, which are not much more massive than the proton and the neutron. What happens is that the energy balance tells you that these particles should be produced. And it's very hard to avoid them being produced if you include them in your modeling. So that's why we know that hyperons should be present in the interior of neutron stars. There are very few things that could prevent that from happening. We're going to talk about one of them soon, which is a very early deconfinement to quark matter. And also we included negative parity baryons, which are again just a little bit more massive than protons and neutrons in modeling of neutron stars. But now, in my opinion, what's the interesting part is, what about if you squish protons, neutrons, and hyperons enough for the quarks in their interior to be deconfined? So this was first proposed in the 60s, first as a hybrid stars that will only have quarks in the very inner core, and also as pure quark stars. And there are several options for including quarks in the stars. For example, instead of having just quarks and hadron with something like a wall around them, you could have also a mixed phase in which you have hadrons and quarks coexisting in the same region in the star. So this was studied again first by Glendening for cold neutron stars, and we also have studied this for the case of proto-neutron stars, in which you also have to worry about having trapped neutrinos. So what I'm focusing today in my talk will be the first case in which you have just quarks and hadrons. Why? Because if you want to measure this, this will be much easier to measure than with a mixed phase. Because if you have a mixed phase, every kind of observable you have for the deconfinement of quarks will be smooth out. So it'll be harder to measure. But there's no reason in principle to avoid a mixed phase. So this is what I mean when I talk about a neutron star. So be careful, because this figure is not in scale. What I call the crust here, the part that have nuclei, the nuclei, these balls here on the left, the circles, it's about 1 kilometer. And the core, it's about 11 kilometers, which is the part in which it's so dense that these nuclei have dissolved into just a soup of hadrons, of protons, neutrons, and hyperons. And in between the core and the crust, you have the very interesting pasta phases in which you form things like matter is so dense that the nuclei start forming funny structures. So people call this long structures spaghetti, just giant, bigger round structures, meatballs. Slabs are called lasagna phase. So you have all these funny structures. But what I'm talking today is I'm going to focus on the description of the core, where you just have, we can think about a soup of hadrons because they don't really form structures. And then in the very inner core, you can have, for example, the confinement of quark matter. But if you don't, you would have a lot of hyperons there, because the more you go inside the star, the higher energy and more you can produce massive particles. So the model that I'm going to use to build the phase diagrams that I'm going to discuss are the Karamin Flu Model, is the Karamin Flu Model, which for the people that are familiar with the NGL, which I know many people here are, or the PNGL, it's similar to a linear sigma model, is also a chiral model, but we have performed a nonlinear realization of chiral symmetry, which gave us more freedom with the couplings. And in this model, I include baryons, nucleons, and hyperons, of course, leptons for charge neutrality, but I also include quarks within the same model. So the way that the degrees of freedom change is through the effective masses of the particles. So in chiral models, the masses for the baryons, for example, are created by the medium. They're created by these condensates. We have a scalar, an isovector, which helps us with having a lot of neutrons, and a strange one. We can have very small bare masses. But I also have this term here related to this field phi, which will become the order parameter for the confinement. So when phi is large, the masses of the baryons become too large and they disappear from the system. And for the quarks, it's the opposite. When phi is large, and large I mean 1, the quarks become too massive and they disappear. So when phi goes from 0 to 1, I can go from having baryons to having quarks. And this is a nice mechanism because it allows us to have very steep transitions between the phases, what we call a first order phase transition, but also is the only mechanism that allows us to have a crossover. Because if you get two separate equations of state, two separate models, and you just match them, you always get a first order phase transition. You always get a derivative. They always have different slopes, which will give you a jump in the first derivatives of your pressure, like the density. But these sort of mechanisms allow us to have smooth crossover going from hadronic to quark matter. We'll also define a potential for this field phi based on the PNGL potential, but I also have chemical potential dependent terms. So this potential is also present at t equal to 0, which is the case for old neutron stars. And this model was fitted to reproduce nuclear constraints around saturation, astrophysical constraints like masses of neutron stars, lattice QCD for the quark part, and I also have check in this agreement with perturbative QCD. So that's all I'm going to say about the model. If you have more questions, you can ask them. But this is the main result of the model. So this is the QCD phase diagram that the model reproduces. So this first order phase transition lines here are reproduced by the model. So we reproduce a liquid gas here at a very low temperature. Although this model doesn't have nuclei, we can tell by the masses of the particles and this chiral condensate where the liquid gas phase transition is. But then we also reproduce these lines here for the first order phase transition between hadronic matter on the left and quark matter on the right. But at some point, these lines end and we reproduce a crossover here with some special properties that we feed it to the lattice QCD properties. And I put some regions here for the people that are not familiar with either particle collision physics or astrophysics. So at the very left here, you have early universe, because in the early universe, although it had very large density, the amount of particles and antiparticles was about the same. So this gives you a zero baryon chemical potential. Also in very energetic particle collisions, the nuclei kind of go through each other completely, and what's left behind cannot create baryon number. So you create this blob of particles and antiparticles at about the same number. So that's why it has a very small chemical potential. But in less energetic particle collisions, some baryon number is left behind, and as a result, you have a larger baryon density, or more particle than antiparticles. So they lie here more to the right, and neutron stars lie here in the very bottom, which are very cold in the MeV scale, although they have about 10 to the 10 degrees Kelvin of temperature. In MeV, this is very close to zero. And it's interesting that neutron stars involve nuclei here in the crust, the core, and also in the inner core quark matter. Supernova are a little bit hotter. They can reach about 30 MeV in the center. So the very young neutron stars, but they cool in about a minute to cool neutron stars. But until very recently, nobody knew where neutron star mergers lie here in the phase diagram. And that will be the rest of my talk, is discussing neutron star mergers and where do they lie in the Qcd phase diagram. But first I want to say that there are two kinds of matter here. In black, the black lines and the black circles are for isospin symmetric matter, so about the same number of protons and neutrons. And that's why you get in collisions, because you collide nuclei, they have about the same number of protons and neutrons. But neutron star matter has about 90% neutrons and 10% protons. And of course, the same number of electrons as protons for charge neutrality. But it's a very different kind of matter, and that's why I plotted here in a different color. And also another thing that I'm going to address in this talk is what happens to the phase diagram when you go from isospin symmetric matter to matter that has many more neutrons and protons. How do these lines move around? And when you move the line around, another way to plot moving this line around, instead of a 2D, plot a 3D Qcd phase diagram. So that's what I'm going to discuss in the next 10 minutes. So I'm plotting temperature. I'm not plotting mu B, I'm not plotting baryon chemical potential. I'm plotting a free energy here, which is a modified baryon chemical potential. And that's the quantity that's the same on both sides of the phase transition, first order phase transition, when we are fixing the charge fraction. The charge fraction YQ is just the amount of charge baryons over your total amount of baryons, and the amount of charge quarks also divided by the total amount of quarks. So I'll give you an example. If you have just neutrons, or twice the amount of down as the amount of up quarks, you have charge fraction 0. If you have the same amount of protons and neutrons, or the same amount of up and down, you have YQ 0.5. Right now, I'm fixing the strangeness to 0. So at equal to 0, you don't have any strange quarks or hyperons. At final temperature, you can have, but as long as the amount of strange particles matches the amount of strange antiparticles. So the total net strangeness is 0. I'll change that later. So this is the phase diagram that you obtain. You see that you can go to the back or the front of the box. This line changes a little bit. I'm going to talk more about numbers later. But what I want to point out now is that when you increase the charge fraction going to the back of the box, you push the phase transition to larger free energies. Or since I'm an astrophysicist, I care about having small charge fraction, many more neutrons than protons, and many more down quarks than up quarks. So what happens is you just pull this phase transition to earlier free energy. And that's very nice because it means it's easier to reach the confinement in neutron stars. And all of these changes are due to what the charge fraction does to the population. So to have more symmetric matter, closer amount of up and down or protons and neutrons, what you do is this matter is more soft. Why? Because remember, our pressure is coming from the Fermi pressure. So if you have just one kind of species, you have very high energy levels because you can only stack one up and one down in each level. But if you have many different kinds of particles, you lower these levels because you open all these new channels with up and down, up and down, up and down, up and down particles, spin particles. So more symmetric matter is always softer. But what I'm checking here is how do I compare the softening that's happening with the hadrons and the quarks, because I'm only looking at the confinement phase transition. So what happens is that the softening is much larger in the hadronic phase. And this has to do with the quantum numbers of the particles. For example, you're comparing having just neutrons to half neutrons, half protons, with having twice the amount of down than up with the same. So the change is much more drastic in the hadronic matter. So hadronic matter gets more soft than quark matter as you move along this line. The change is larger. But the thing is, I'm talking about soft and stiff, talking about pressure versus energy density. But if you talk about pressure versus free energy, it's actually the opposite. It doesn't have to be the same. So what happens is larger pressure or a larger softening in P versus epsilon means less softening in pressure versus free energy. So that's why as the matter gets more isospin symmetric here towards the back of the box, the hadronic matter extends to larger free energy. But many people are familiar with baryon chemical potential, not free energy. So here I show how the same phase diagram look as a function of baryon chemical potential. It's kind of interesting that looking at the red first for the quark side, now they're different. The hadronic and the quark side are different. So that's why I didn't want to show this at first. The quark side, the red box is very similar to the brown one. And that's because the free energy differentiates from the baryon chemical potential by YQ versus times mu Q. And mu Q is very small. The charge chemical potential is very small in the quark phase. But in the hadronic phase, the charge chemical potential can be very large. I mean, negatively large. So this makes the baryon chemical potential and free energy different. So that's why the green box is different from the brown box. And you can think about the charge chemical potential as the difference between up and down quarks or protons and neutrons. And again, the difference between up and down quarks is never that large as you move to the front and back of these boxes. But the difference between the amount of protons and neutrons is much larger. But so far, I was only talking about matter with no net strangeness. But neutron stars can have a lot of strangeness. Why? Because they evolve for millions of years and you have plenty of time to create strangeness. So what happens is things change a little bit. So first, but because I want to show too many lines now, instead of showing phase diagrams that are 3D, I'm just showing you now the bottom of the box. Okay, just the bottom of all those boxes. So I put here the bottom of the box that we had, which is the brown line for the free energy, and then the green and red for the baryon chemical potentials. Now I'm adding black lines for matter strangeness. Well, around the confinement phase transition, we shouldn't have strange quarks. And that's because strange quarks are more massive and only appear later. So the only strangeness here that's appearing, if you allow it to appear at equal to 0, so I'm only talking about the bottom of those boxes, is a little bit of hyperons that appear in the hadronic matter before the phase transition. And the thing is that hyperons are suppressed at large charge fractions. So nothing changes in the right side of this plot because the hyperons are suppressed by having a lot of protons at large charge fraction. Hyperons only appear at small charge fractions. So that's why strangeness is affecting this plot just a little bit. So the black and the colored lines are a little bit different. In the brown and the black lines are a little bit different in the left side of the box. For the chemical potentials, again, this is just a shift that you get. But I'm more concerned about the free energy here, which changes in the left of the box. And now I'm going to look at the top part of the phase diagram. So this is the top of the previous phase diagram. And this is more interesting because now strangeness changes everything. Why? Because at large temperature, I'm looking at the top of the line when the first order phase transition is about to become a crossover. What happens is that you have a lot of strange quarks around the confinement and a lot of hypers. And what happens is that because we have a lot of strange quarks, we make quark matter softer in comparison to not having strangeness, much softer than what's happening in the hadronic side. So therefore, these lines are pushed to larger chemical potentials and larger free energy. So that's why these black lines are shown above. So the phase transition is harder to be realized here if you have a lot of strangeness. And so far, I only had charge fraction in the bottom of these figures. So now I added two new figures here in the bottom side of the slide, which shows the isospin fraction. Because I know that many people here are interested in high energy physics and particle collisions. And in high energy physics, people usually don't discuss charge fraction, they discuss isospin fraction. Their shift is about, if you look at the formula on the top, is about 0.5 if there's no strangeness. So if there's no strangeness, charge fraction of 0 means isospin fraction 0.5. Charge fraction 0.5 means isospin fraction 0. But the thing is, when you add strangeness, this formula becomes non-trivial. So for the colorful lines here that I have shown you before, these plots on the bottom compared to the plots on the top are just a 0.5 shift. I'm just shifting the axis, the x-axis by 0.5. But for the black lines that have strangeness, this is not a trivial shift. The shift is more complicated and depends on the amount of strangeness you have. And the amount of strangeness you have depends on the temperature, depends on the baryon chemical potential, depends on the charge or charge or isospin chemical potential. So the shift you get is not trivial. But again, at zero temperature, the bottom left plot will only be shifted, have a large shift where there's strangeness, which means small isospin fraction. But if you look at the bottom right plot, this shift happens everywhere because now there's strangeness everywhere. So the black lines have a very weird shift. And you can even end up with positive isospin fraction here in order to have the 0.5 charge fraction. So that's what I mainly wanted to say about 3D phase diagram. So as a very quick review, in heavy ion collision, the charge fraction you have almost isospin symmetric matter. It's between 0.4, 0.5. In neutron stars, you have very small charge fraction, actually close to 0. In supernovae matter, it's kind of tricky because although this lasts for a minute, lots of things happens in this minute. And this is a very large region involved. But the canonical value that people like to refer for supernova is 0.4, because that's what happens more in the core in the earlier times. So again, it's almost isospin symmetric matter. And the question is, what about neutron star mergers? And that's the answer that's the question we're going to answer. And neutron star mergers became very popular recently. People are talking a lot about them because if you think about it, we were just looking at the universe, seeing light for thousands of years. Everything we knew, except for a little bit information from neutrinos, but most of what we knew was just looking at light. And light is even something complicated to measure. It doesn't sound like at first, but because our atmosphere blocks most of the light. It lasts through visible light and a little bit of radio, but everything else you need to send probes to space to measure it. But gravitational waves don't have to deal with that, don't have to this problem. So we can build interferometers here on Earth. And the first neutron star merger was measured by LIGO, and in a way with Virgo, because Virgo didn't measure the signal, but this also helped to locate it in the sky in August of 2017. So it's a very far away merger that took place hundreds of millions of light years away, and it was measured by a lot of observatories in light, but only LIGO in gravitational waves. And we performed some simulations. These simulations were performed in Karamin field equational state. And these are not in chemical equilibrium. So you have to make 3D tables for the simulations to be performed. You have to provide an equation of state that changes in density, temperature, and also charge fraction. And I provided an equation of state with quarks and one without quarks. And the group of Luciano Rezzolla in Frankfurt used their full general relativity hydrodynamics code to evolve this merger. And what they found out is that we could clearly see a signal for quark matter in the post-merger part of the signal. So we chose mergers of around 1.4 neutron star each. This is about what we measure from the signal that I showed in the previous slide. And this is very interesting because we only form quark matter substantially in the post-merger part. So in this case, I'm showing here two slightly different masses. What happens is that when the density and temperature are high enough for a phase or the phase transition to take place, the star collapsed to a black hole much earlier than it would if there was no phase transition. So you see the reg signal here lasts for about 5-7 less milliseconds. And it's not just the duration of the signal, we also change the frequency and the amplitude of the wave. And here you can see a graph of the phase difference between these two gravitational wave forms. So if we detect the post-merger part of the signal and it's much shorter than expected for the pre-merger signal that you have, this is an indication of first order deconfinement to quark matter. But the problem is, go back, I think I have, sorry, I have the slide somewhere here. This part of the signal that we're talking about hasn't yet been measured, but LIGO and Virgo are hopeful that it will be able to measure this part of the signal soon. So what actually happened in the merger is, here we're looking at different times, is that you have two stars that merge. So here you have the reminiscent of the original stars, which forms a sort of ring here, this dense and hot ring that already has a little bit of quarks because it's hotter. But then at some point, when you trigger enough density and temperature in the center, you deconfine to quark matter and you have a lot of quarks in this inner region that is shown here in white, meaning very hot and with lots of quarks. But my question was, how does this look in the phase diagram? So to answer this, we thought it'd be nice to have a background in this plot, just to tell you, to guide you, to guide your eye to know how many quarks, how much quarks you have. So at equal to 0, the Karamin Flu Model predicts just hadrons on the left and just quarks on the right. So it's white here on the right. But as you go up in temperature, you start having some quarks in the hadronic phase and some hadrons in the quark phase. And this is necessary because if you keep going up in this plot, you see that there won't be any difference between the hadronic and the quark phase. And I put everything being light yellow. This fuzzy line here between the two phases, because you're looking at baryon chemical potential and not free energy. So there's some funny discontinuity that appears here. In order to show you this, I had to choose a specific charge fraction, but when you change charge fractions, as you already learned in the previous slides, these colors will change a little bit, it will shift a little bit to the right, a little bit to the left. But I had to choose a background here. And now this is the result of the 3D Karamin field equational state in the merger. So I cannot show you everywhere at all times because you'll be too messy. So first I decided to show you only a specific time. So I show you all the merger at 5 milliseconds after the merger happens. It's still before collapsing to a black hole because unavoidably this will collapse to a black hole because you cannot have neutron star masses with 2.9 times the mass of the sun. So what happens here is that the merger, and as you go towards the center, this blue gets more dark. So here you have the outside part of the merger in light blue. And then at some point, remember we discussed, you have this hotter ring, which is this part that's hotter here. We call this the wing of the swan. And as you go more towards the center of this hypermassive neutron star that you form, at some point, you pass this threshold for the confinement. And at that point, your temperature increases substantially, and then you continue increasing density on the other side of the phase transition. We call this the head of the swan, because some of our collaborators pointed out that this looks like a bird. But there are other things we can do. Now, instead of looking at specific time, we can also look at different times. But in order to do that, we choose 2 points. We choose the maximum temperature or the maximum density. So the maximum temperature first is that ring more outside the center. And this is shown here by the spheres on the left. You have that hot ring. That's the hottest part. And but as time passes by, so these circles get darker here. As time passes by, at some point, the center of this hypermassive star goes through the phase transition and gets much hotter. So that's why the hotter part jumps from the ring to the right here. You'll have the center of the merger. What about tracking the densest part? Well, the densest part is always the center. The densest part, as these diamonds get darker, they just get denser and hotter. So this was the first time someone showed neutron star merger in the phase diagram. It is interesting to see that we can get the temperatures up to larger than 60 MeV, and we can get to chemical potentials larger than 1400 MeV, which is incredibly large, even for a neutron star. What about the other quantities that we've been discussing? So we discussed the charge chemical potential. So the charge chemical potential, as you go towards a normal neutron star, it gets more negative. So we think about going right here, going towards the center of a neutron star. But this is not a neutron star. This is a hypermassive neutron star that you form after the merger. So what happens is at some point, you reach the threshold for the confinement to quark matter. And remember, quark matter has a much charge chemical potential much closer to 0. So what happens is this is the first order phase transition here on the left plot. And then the line here on the top of the plot means that that's where quark matter lies. And for charge fraction, which is related to the charge chemical potential, we wanted to see which kind of conditions do we get in this kind of merger. So we had a charge fraction that was increasing going to the center of the star. You can think about going right to the center of the star. But what happens is that the phase transition decreases the charge fraction. Why? You see, decreasing the charge chemical potential is also decreasing in absolute value, decreasing the charge fraction. So the conclusion here is that you're never going to achieve the conditions in proto-neutron stars in a neutron star merger. So neutron star mergers are hotter, so it looks like supernova matter, but it's never going to be the same because the charge fraction is much smaller. You have much larger amount of neutrons or down quarks. And I have time, I'll show you the simulation here. So this is the results of the simulation I just showed you. So let me change. I'm going to send you a copy of the PowerPoints. And then you can just click on this and you get the link to the YouTube video. So the simulation starts with 2 neutron stars that start getting deformed as they get closer and emit a lot of gravitational waves. And then the merge takes place. And now this color code tells you about the amount of quark matter on the right, more yellow is more quarks, first around the ring, and then you get a lot of them in the center. Now I also have temperature. And of course, a lot of things happen outside that core, but the core is what I'm focusing on because the core of the hypermassive neutron stars is where we have all the large density and temperature. Let me share again my normal screen. Can you see my normal screen again?
Yes. Yes.
And a little bit more about what's happening in this merger. For again, the people that work with heavy ion collisions that are used to talk about entropy per baryon. So here in this left side of the left plot, I show you the entropy per baryon at 5 milliseconds after the merger. And you see that the entropy is much larger in the center. We can reach entropies of about entropy per baryon of about 3 or 4, depending on the specific conditions, which is comparable to heavy ion collisions, and temperatures too, talking about lower energy heavy ion collisions. And but again, the collisions are never exactly the same because the charge fraction is very different, and the strangeness too. I have a lot of strangeness, which is shown here in the right plot. And on the left side, I'm showing general amount of strangeness, and the right side of the right plot, just quark strangeness. So the strangeness is always large in the center, but outside the center, you have a lot of strangeness coming just from the hadrons. The difference is that when you get to the inner core, it switches from being strangeness from the hadrons to being strangeness from the quarks. And again, going back to that picture that I showed you before, although this is very interesting, at the moment, we cannot look at the post-merger signal and tell you what's happening, which is where we form a lot of quark matter given this equation of state. But what have we learned from mergers, nuclear physics-wise? So now I'm showing a couple of slides that discuss the neutron star mergers that we measure and the information that we obtain from them. So the first one, the one that everyone is 100% sure was 2 neutron stars, because we also observe a lot of light from this one, is GW170817. In this one, we measure the tidal deformability because that's something that has to do with finite size effects influencing the first part of the merger, which is deforming the stars, because larger stars will deform much more. And what we found out is that the formation was not very large, meaning the stars were not very large. So this is a indirect way to measure the radius of neutron stars. But what we investigated is how different equations of state can reproduce different tidal deformabilities. And what I found out is that if you use very standard interactions, just like one scalar for attraction, one vector for repulsion, and these are very simple interactions and very common that most people use in their models, we have a large tidal deformability and a large radius. Different models have slightly different ones, but they are larger. But if we include a new vectorize a vector kind of interaction, which is a Lagrangian term like this that can be included in any model, can be included in the Valechka model, it can be included in chiral models, in quark models. What we found is that this kind of term decreases within one model. I show you here for 3 different models. It decreases the tidal deformability or the radius of a 1.4 solar mass star, which is what people got the measurement for in GW170817. So, well, my message here is that the measure of tidal deformability does not exclude models, but it tells us more about hadronic interactions. And why hadronic and not quark? Because you probably do not have quark matter at the densities reaching a 1.4 solar masses star. I mean, it could be if your whole star is quark matter. So there is a possibility. But I think we can say that we learn much more about hadronic models. Why? Because quark models reproduce small stars with tighter deformabilities anyways. But these stars made out of quarks at these densities, which probably is, we can learn more about these interactions. And I want to say a couple more things here. So this kind of interaction was first suggested by Horowitz and Pikarovitz to describe better agreement with neutron skin. And we actually have looked at it, and this kind of interaction also help us to be in better agreement with Kara effective field theory calculations, which give us more information about the equation of state at low densities until about 2 times saturation density. What about more gravitational waves? So we have information from LIGO and Virgo about more events that could or could not have been neutron star mergers. And the reason for that is that there was no light observed from these events, so we cannot be certain they were not just black hole mergers. This one in particular is interesting because it was the merger of a black hole. How do you know it's a black hole? Is because it has more than 20 solar masses, with something that could be either a black hole, a very light black hole, the lightest one ever observed, or a very massive neutron star, the most massive one ever observed. So my question here is that if this is a neutron star, can we model it as a hybrid star? And the answer is yes. But again, this teaches more about the interactions in these stars, because for this to be the case, you have to include vector interactions in quark matter that so far in the Kara model we had not done. And when include, because neutron stars without quarks, you can reproduce larger masses, even with hyperons, but when you have a first order phase transition, it locally softens your equation of state, so it's harder to reproduce hybrid stars that still have a substantial mass, because we have to reproduce at least 2 solar mass stars and cold neutron stars, because we know that those exist. So if you see here, the blue lines are shown in green here in this mass radius plot when the first order phase transition takes place. But what we found out is that if we include vector interactions, vector interactions for the quarks, and also vector interactions in the mean field that mediates interactions between hadrons and quarks, we found out that we can increase the mass, even in phase transitions in realistic models, all the way up to 2 solar masses, above 2.1 or more. And when we include rotation, and this is the plot on the right, I'm just showing for one case here, for a hybrid star. The bottom part of the right plot is a non-rotating star, but as you add angular momentum here, you change the color all the way to the Kepler frequency, the maximum frequency the star can rotate without shedding mass. We can reproduce stars with mass of about 2.5 solar mass, which is the bottom of what was measured here for this event, and still have a reasonable amount of quarks and a large amount of hyperons in the center. So here on the right, I show you mass of the stars against central density. So if you have a star with a central density of, for example, 1 Fermi to the -3 here, you can have about 2.5 solar masses and still have a large amount of quarks. Because if you pass the vertical line for quarks here going to the left, you don't have quarks, and the second line here going to the left of the hyperon line, you don't have hyperons. but you can still have an island here on the right where you have hybrid stars. So this could be a hybrid star event. And I forgot to say here, on the last plot, I put 2 gray lines here that just show you what happens when you change the vector isovector previous interaction that I showed in the previous slide. So in increaser interaction, you change the radius of that star. Larger interactions mean smaller stars. Do you guys have any questions before I go on?
So is there any question? No, it seems not.
So
Okay.
Then I get to my conclusions. I think that astrophysics provides an ideal testing ground for nuclear physics. The conditions created in neutron star mergers are very unique. They are not the same conditions as cold neutron stars. They're not the same conditions as supernovae. They are not the same conditions as heavy ions. So this is a whole new way of studying matter with very specific conditions of having leptons, having strangeness, but having a small charge fraction or very negative isospin fraction and being hot. I also discussed that charge fraction, isospin fraction affects significantly where the confinement line is in the phase diagram. For example, baryon chemical potential can change up to 130 MeV, and charge chemical potential or isospin chemical potential by up to 330 MeV when you change the conditions from 0 to 0.5 charge fraction. So we have to be very careful when we compare the confinement in heavy ion collisions or in neutron star mergers or neutron stars, because we have to move this line around when you're making comparisons under different conditions and also of strangeness. Now we're living in very interesting times, because besides looking at light, you can also learn about the universe of gravitational waves. So I think as soon as we start measuring the post-merger part of the gravitational waves, we will be able to hopefully find signals for first order phase transition to quark matter. If this is a first order indeed, because some people say it's not, but hopefully it is, because it's just easier to observe. If this is a very smooth crossover, it'll be very hard for us to observe, but I'm hopeful it's not, and we'll be able to see this soon, and it'll be very interesting. But in order to learn more about simulations, and also from data that comes from LIGO and Virgo, we have to have very realistic models to be able to make predictions, not only for merger simulations and waveforms, but also to understand what tidal deformability really means. And if you can indeed exclude equational state models or exclude certain degrees of freedom from this data. And that's all. Thank you.
Okay, thank you very much for this nice talk. So the session is open for questions. Is there any question? So, any question?
I have one question, but very, very simple
sure.
one, very naive.
Yeah.
Because I don't work in neutron star. The thing is that I heard that neutron star is made of neutrons mostly. But what conditions make them are required to form a neutron star?
So let me go to my neutron star slide.
What about the strong interaction between neutrons, repulsions, and everything?
So depending on the mass of your star, initial mass of the star, it went up its life as a white dwarf, a neutron star, or a black hole. So for example, our sun is a very common star, which is lighter. So after the sun runs out of fuel for fusion, you'll become a white dwarf. But more massive stars, more massive than about 10 times the mass of the sun, will at some point run out of fuel and then they start collapsing because they cannot fight gravity anymore. And the more massive the star, more strong this collapse is. And this collapse can compress matter much more. And when you compress matter is when quantum mechanics really kicks in. And when you compress these neutrons, and at this point you have also a lot more protons. But during this compression, many of the protons will capture electrons and become neutrons. So during this collapse, the neutrons will get so closer to each other that this Fermi pressure will become enough to hold the collapse, and this will become a neutron star. If the star is too massive, nothing can hold this collapse, and it becomes a black hole. So then you form the neutron stars. So the neutron stars will have this original layer in which you had the nuclei, protons, neutrons, and electrons, and normal stars have. But neutrons are special because that's when you compress matter enough to produce this core, which is the soup of protons, neutrons, and electrons. And when you have enough energy in your star, because as you compress more and more towards the center, your energy is larger, you have enough energy to convert, for example, a neutron into a lambda, which is instead of having just ups and downs, you also have strange quarks inside. So that's what makes them heavier, because strange quarks are heavier. And then you will start producing more and more of these hyperons. As you go to the center, you produce more and more heavy hyperons, unless you have the confinement to quark matter, which then you just dissolve all your protons, neutrons, and hyperons into quarks. I don't know.
You also have the other quarks, not only strange, right?
You don't have enough energy to produce heavier quarks like charm, at least not at zero temperature. But even at final temperature, it'll be very hard to produce, because then the charm is already too heavy, and the other ones are crazy heavy. So in principle, neutron stars should only have up, down, and strange quarks, or mergers too.
Thank you.
But there are other particles that I didn't mention. Like, for example, in the very beginning of my talk, I also mentioned particles that have negative parity that can also appear in neutron stars, which are heavier than protons and neutrons. And there are other kinds of matter that I didn't discuss in detail. For example, your mesons can condense, and there are lots of interesting things that can happen.
Okay, any other questions or comments? So I have also a question. You are in the region of also for your chemical potential, the region where you have your neutron stars are is not so big. So you have actually probably. I mean, what's the role of the other kind of condensates, like the color superconductivity, the diquark condensates, and so on, in this kind of neutron stars?
So I do not study pairing. It's very important, and a lot of people do. And the reason for that is that the pairing changes a lot the evolution of the star. Because whenever you have pairing of hadrons or pairing of quarks, these particles won't participate in the reactions that cool the star. So pairing is essential for the evolution of the star, especially the thermal evolution, but also many other interesting effects. But the thing is that the pairing doesn't change things that I study, for example, a lot, which is the mass and the radius. If you calculate the corrections, they'll be very, 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 very tiny. But they're very important. It's just that if for example, here, the hadronic phases will be divided into different phases, they are paired or not. All this quark space here will also be divided in many different phases depending on the pairing.
Yes.
But I don't study that.
And another question is, what's actually the role of rotation? The rotation of the quark, the neutron stars, the velocity is very large. Yeah.
But most of the stars don't rotate as fast as what's necessary for changing the particle composition. Again, all stars have magnetic fields, but most stars have magnetic fields that's not large enough to change the composition. So what happens is that when a star rotates, the central density decreases. You can just think, you know, a bucket of water moving along, and at some point the water will all spill. And the central density decreases. You can think about, going back to my slides, as, you know, just going left, having the slides changing, shifting to the left, and you won't reach such central densities. But you have to rotate really fast for this to be the case. And then your central density to decrease enough, or again, a magnetic field has a very similar effect. If your magnetic field is very strong, you decrease the central density of the star in a way that you prevent quarks from appearing. So different models have different threshold for the appearance of quarks. But no matter what, if the star is rotating incredibly fast close to the Kepler frequency, or have very strong magnetic fields, you at least decrease the amount. In my model that the quarks appear early in the plot I show you, you have less quarks. You don't fully, for a massive star, you don't fully prevent the quarks from appearing, but the rotation decreases a little bit the central density of the star. But even in this case, I think what's interesting is that as time passes by, rotation starts spin down because they lose energy. Either they spin down or the magnetic field decays. So eventually, in principle, if they don't merge or something like that, all stars should have their densities increased enough for, if not the quarks, at least the hyperons to appear.
Okay, thank you. It seems that there is another question by Ali Tabatabai. So Ali, do you want to ask by yourself? He's not here. Okay, I think he has lost the connection. Okay. So he writes, does magnetic field change the results significantly?
If they're magnetars, which are the magnetic fields that have incredibly high magnetic fields, up to 10 to the 15 Gauss on the surface, we have to talk about very large magnetic field. Then it can have the same effect of decreasing the central density of the star and preventing some, or depending on the model, all the quarks to be there. But again, the magnetic field will decay over time unless something happens, like a merger or accretion.
Okay. Thank you. It seems that there is no other question or comments. So thank you very much, Veronica, and nice to have you here. And nice to have everybody else here. And now it's time, I think, for some informal discussions. I think, Masoud, do you want to say something?
Thank you. I will stop the recording, and I have an announcement to make.